Hello students, let us start our today's session from the chapter Organic Compounds Containing Nitrogen. The last session we completed the preparation and properties of nitroalkanes and nitroarenes. So in that session just missed out the preparation of nitrobenzene and the electrolytic reduction of nitrobenzene. Let us complete this part and then we will start with amines. Preparation of nitrobenzene. Nitrobenzene that can be prepared by direct method as well as indirect method. In direct method, the benzene that can be nitrated in presence of concentrated nitric acid and concentrated sulfuric acid. So, one of the hydrogen in the benzene that can be substituted by the NO2 group. So, we are getting nitrobenzene and water. Here, the nitrating mixture is concentrated sulfuric acid and concentrated nitric acid. Suppose, if the nitrobenzene is further nitrated, because we have taken the mixture, that mixture it can proceed further reaction of nitration of nitrobenzene. So when nitrobenzene produced is nitrated further, we are getting meta-dinitrobenzene. Why we are getting meta-dinitrobenzene? Since the nitro group is electron withdrawing group and hence it becomes a meta-directing group. So that's why the meta position hydrogen is once again substituted by the nitro group. So we will get meta-dinitrobenzene. So by direct nitration of benzene we can prepare nitrobenzene as well as meta-dinitrobenzene. The second method is indirect method, in which amines are converted into nitrobenzene. If we take amine alone, that can be converted into diazonium salt followed by treatment with the sodium nitrite. It may give the nitrobenzene. But in this case, we are going to prepare para-dinitrobenzene. So, meta-dinitrobenzene is prepared by direct nitration of benzene, but para-dinitrobenzene is prepared by taking para-nitroaniline. So, first of all, the amine group is diazotized. Usually, diazotization takes place in presence of sodium nitrite and HCl. Here, instead of HCl, we have taken HbF4, hydrofluoroboric acid. But this complex, it is stable at room temperature. The fluoro derivative is stable at room temperature and hence we do not mention the temperature as 273 to 278 Kelvin. So when para-nitroaniline is treated with HbF4 in presence of sodium nitrite, actually that forms NaBF4. Both will react to give NaBF4 as and HNO2. And hence the amino group is converted into diazonium fluoroborate. Followed by treatment with the sodium nitrite, the entire fluoroborate is substituted by the nitro group. So we are getting para-dinitrobenzene as well as BF3, NAF and nitrogen. Oxidation of para-diaminobenzene. The para-dinitrobenzene that can be even prepared by taking para-diaminobenzene. This oxidation that can be carried out either in presence of trifluoroperoxyacetic acid or Carose acid, H2SO5 is called Carose acid, or peroxysulfuric acid, that is H2S2O8 is called peroxysulfuric acid. So either of trifluoroperoxyacetic acid or Carose acid or peroxysulfuric acid, both NH2 group that can be oxidized into para-dinitrobenzene. So that's all the preparation of nitrobenzene by direct method as well as indirect method. The next one, The last session we discussed about the reduction of nitrobenzene in different medium, acid medium, alkaline medium and neutral medium. Besides that, the nitrobenzene can also be reduced in electrolytic medium. In electrolytic medium also we can take weakly acidic condition or even strongly acidic condition. So when this nitrobenzene is electrolyzed in presence of weakly acidic medium, the NO2 group is converted into NH2. So the reduction takes place. So both the nitrogen is being removed as 2 molecules of water. So this reaction involves 6 atoms of nascent atoms of hydrogen. But in the case of strongly acidic medium, the NO2 group we can represent as NOO. So only the NO group gets reduced to NHOH and this oxygen is left as minus H2O. So totally HH plus 2 hydrogen. This reaction involves 4 hydrogen atom. So this forms phenyl hydroxylamine. This phenyl hydroxylamine, it undergoes rearrangement with para position. Para position actually it has hydrogen. So the hydrogen that can be attacked by the NH group and the OH group is being attached to its para position. So we are getting para amino phenol. So electrolytic reduction of nitrobenzene can be done in 2 different medium. One is weakly acidic and other one is strongly acidic. So weakly acidic it gives aniline, but strongly acidic that forms para amino phenol. That's all the topics we covered from nitroalkanes and arenes. The next topic from organic compounds containing nitrogen is amines. Amines is an essential derivative of ammonia actually. Ammonia, it has 3 hydrogen atom. All these 3 hydrogen atom that can be replaced by either alkyl group or aryl group. So it gives rise to the derivative of ammonia. Why do we learn about amines? See, amines that play the most important role in the manufacturing of polymer industry or even the pharmaceuticals also, as well as it is present in biologically active compounds like adrenaline and ephedrine. So both of them, they contain secondary amino group. And most of the living organisms, they have one or other the nitrogen containing compounds. That could be a nitro derivative or even amino derivative. So let us start with amines. Amines are the derivatives of ammonia. Ammonia formula is NH3, where the nitrogen, it has an unshared pair of electron called lone pair electron. So in ammonia, you can replace either one hydrogen or even all hydrogen. That gives rise to primary amine, secondary amine and tertiary amine. So when the hydrogen atom of ammonia is replaced successively by either one alkyl or 2 alkyl or 3 alkyl, we will get the class of primary, secondary and tertiary amine. And this NH3, it can also react with the acid like HCl. It forms the salt NH4Cl. So why do it reacts with the acid? Because ammonia is a weak base and hence it reacts with the strong acid to form salt. In the salt, it has 4 hydrogen atom. So like ammonium chloride like structure can also be formed by using alkyl group. So we are getting tetraalkyl ammonium chloride. It is said to be quaternary ammonium salt. So besides primary, secondary, tertiary, we can have quaternary salts also. That's all the class of amines that can be formed from the ammonia. So let us classify amines. Amines can be broadly classified into aliphatic and aromatic. Aliphatic, the group it will be R group, and in aromatic the group will be AR group. So when hydrogen atom of ammonia is replaced by an alkyl group, we will get aliphatic amines, or if the hydrogen atom of ammonia replaced by the phenyl group aryl, that is we are getting aromatic amines. So generally aliphatic amines are represented as RNH2 and aromatic amines are represented as AR, aryl NH2. And this aliphatic amine that can even be further classified into primary, secondary, tertiary. Depends on the number of alkyl groups attached to the nitrogen atom. So in other cases and all, we discussed about the number of alkyl group attached to the functional carbon gives rise to primary, secondary or tertiary. In this case, here the active case is ammonia. So from this ammonia only we are getting the derivative, and hence with reference to nitrogen only we can say how many alkyl groups are present, and according to that we are classifying primary, secondary and tertiary. So in the primary amine we know only one alkyl group is present. Whether it is functional carbon or even the amine, that is not the matter. You have to find how many alkyl groups are there to the functional group. So to the functional group NH2 I have only one methyl group. So the name is methylamine and it becomes primary amine. And in the other case it has an alkyl group only one, that is ethyl. So it becomes primary amine. When I take secondary amine, that can be further classified into simple and mixed. Simple means both the alkyl group will be the similar. Mixed, the alkyl groups that can be different. See, in the simple dialkyl amine I have dimethyl amine. CH3, CH3, both of them are similar groups, so this can be a dimethyl amine. But in the mixed one is methyl group, the other one is ethyl group, and hence in the secondary amine we can have the mixed amines also. So this becomes ethyl methyl amines. Similarly, you can classify even tertiary amine as simple and mixed. So tertiary, the functional group should have 3 alkyl group. So this is the nitrogen, it is a functional group. In the case every hydrogen atom is being replaced by the alkyl group. So when all the hydrogen atom of ammonia replaced by the alkyl, we are getting tertiary. So CH3 thrice N. So all the alkyl groups are similar, and hence it is said to be simple tertiary amine, and the name of the compound is trimethylamine because all of them are methyl group only. And in the mixed case, one is methyl part, other one is ethyl part, and the third one is propyl part. So 3 different alkyl groups are there, or even 2 of the alkyl groups are different, that it comes under mixed one. So here the name will be ethyl methyl propylamine. Ethyl methyl propylamine according to their alphabetic order. Similarly, aromatic amines also classified as simple and mixed. In simple amines, the aryl groups alone be present, but in mixed amine, it can have an aryl group as well as alkyl group. So primary amine that can have only one ring to the ammonia. So we are getting C6H5NH2. So in primary amine, that ammonia molecule in which one of the hydrogen is replaced by only one phenyl group. So we are getting C6H5NH2 called aniline. And in secondary amine, we can have simple and mixed. Simple, both the groups will be the same. So we have diaryl amine. How many phenyl are there? 2 times. So the name of the compound is diphenyl amine. And in the case of mixed one is phenyl, the other one is methyl. So we have to say methyl phenyl amine. So we have to take the name according to their alphabetic order only. So we are getting methyl phenyl amine. And in the tertiary amine, once again simple and mixed are there. In simple, all the ring R, all the hydrogen atoms are replaced by the phenyl group. So we can say it is a triphenylamine. And in the mixed one of them is ring, the other two are alkyl. The two alkyl can be similar, or even you can take the different alkyl. Whatever it is, you have to write what about its name, either ethyl methyl phenyl or dimethyl phenyl. See, it is dimethyl I have, so I can write dimethyl phenylamine. So that's all the classification of amines. Nomenclature of amines. So in nomenclature, the common name is usually alk plus yl plus amine. So alkyl amine. In IUPAC, you can say whether the amine group as the prefix or even the suffix. When you take amine as prefix, the name is aminoalkane, or if amine is taken to the suffix, it is called alkane amine. So in this case, most of the names I have given in suffix only. The first case is methane amine. So in this methane amine, it has only one carbon, so it is methylamine as common name, or IUPAC prefix, it has no prefixes, only one carbon, so meth saturated ane, and hence the name is methane amine. And in the next case, it has two carbon atoms, so the root word is eth, so ethane amine it makes, but the common name alkyl amine, and hence ethyl amine. When we go to the carbon more than 2, where you have to find the position of amine group, that is essential. See that I have 3 carbon in a chain, it has no branches, that's why the common name is N-propyl amine. The N indicates the chain has no branches. 3 carbon are there, so the name is N-propyl amine. And its IUPAC name, where amino group is present at the first carbon, so I have to take the locant number, so the name is 1-aminopropane or propane 1-amine or 1-propane amine. You can write this position 1 either in between of alkane and amine, or even in before of the alkane amine also. So in both the way you can represent the position of the amine. And in the next case, I have taken isopropyl. See, CH3, CH3 structure is always isopropyl structure. So this is common name, I can say isopropyl amine. But in IUPAC, the position of NH2 changed. So once again, giving the numbering, so we are taking 2-aminopropane. So the name is 2-aminopropane or propane 2-amine. Both of them are correct. So I have given here propane 2-amine. First cases and all, I have taken only the NH2 group. NH2 is the part of primary amine. So all these 4 under the class of primary amine. And in the next case, I am going to take with the secondary amine. Secondary amine, one more hydrogen atom of NH2 group will be substituted by some other alkyl or aryl group. In this case, N-methyl and I have ethyl group. So when you give the common name, you should follow alphabetic order. So it becomes ethyl methyl amine. IUPAC name, you should find the longest chain. The longest chain should have more number of carbon. So the chain that makes ethane, and the methyl, it is attached to the nitrogen atom. So you have to indicate the methyl to which it is present. It is present with the nitrogen, and hence I am writing N-methyl. Since the methyl that can even be the part of the substituent of alkyl chain. So to differentiate whether the alkyl group is as a part of chain or to the substituent of nitrogen, that is what distinguished by taking N-methyl. So it indicates methyl is present in the nitrogen. It is attached to the nitrogen. So the name is N-methyl ethane amine. So when I take the 3-methyl group, it is a tertiary amine. This is a secondary amine, it is a tertiary amine. In the tertiary amine, all the 3 alkyl groups are similar, so I can count 1, 2, 3. So the name, common name becomes trimethylamine. But IUPAC name, only one alkyl part that makes the parent hydrocarbon, the other alkyl part that makes part of the nitrogen. So as all the methyl groups having only one carbon, so one of the methyl is taken as the parent chain. Other methyl group that becomes the part of nitrogen, and both of them are same. So instead of writing N-methyl, I can write N, N dimethyl. So the name is N, N dimethyl methane amine. And in the next case, you may find it has a methyl group, ethyl group as well as a propyl group. So methyl, ethyl, propyl. So the longest chain should have the hydrocarbon part, and hence this propyl that makes the part of the chain. And to the nitrogen, it has two different alkyl group. One is methyl, other one is ethyl. So here we can't write N, N. Instead, you should write N-ethyl, N-methyl in alphabetic order. So the prefix it comes N-ethyl and N-methyl. Okay, and this group, it is the chain, but the nitrogen is attached to the second carbon of propyl. So 1, this is 2, this is 3, and hence we are writing it is 2N-ethyl, N-methyl, propane amine. So that's all, and these two represent nitrogen to the second position of carbon. N-ethyl, N-methyl, it says nitrogen, it has one ethyl group as well as a methyl group. The next one, let us go with aromatic amines. In this only one benzene ring is there, so it is common name, its common name is aniline, or IUPAC name you can say aminobenzene, or even you can write benzene amine. But in IUPAC system, the common name aniline is itself taken as IUPAC name, so you can consider C6H5NH2 as aniline. And this is a primary amine, so I can go with its secondary amine also. It is secondary amine, this is a tertiary amine. In secondary amine, nitrogen has methyl, so common name methyl phenyl aniline, but IUPAC name N-methyl aniline, or else N-methyl benzene amine, or N-methyl aminobenzene, whatever it is correct. And in the tertiary amine, the nitrogen, it has two similar methyl groups. So it is taken N, N dimethyl. It is attached to the benzene amine. So the name is NN dimethyl benzene amine, or instead of benzene amine, you can even write aniline. That's all the nomenclature of amines. So when you write common name as well as IUPAC name for the amines, you have to give more attention to which the alkyl group is present, whether as a substituent of the longest chain or as the substituent of nitrogen. When it becomes the substituent of nitrogen, then you have to specify as N-alkyl, or it is to the part of the chain where you can simply write to which carbon it is present. So here I have taken very simple examples only, but with respect to this compound, you can have more number of structure because I have taken only propyl. In the place of propyl, you can give butyl. The butyl can be given like N-butyl, isobutyl, secondary butyl as well as tertiary butyl. So whenever the butyl isomer it forms, according to that its common name as well as IUPAC name will be changed. So you can practice this with butyl. And moreover, most of the questions, IUPAC questions, are asked from amine chapter only. This is why, because all other chapters, they have a pattern of IUPAC name structure where we are finding the functional group or the functional carbon, we are completing the name. But in this case, the functional group is amine, and to which the more primary, secondary, tertiary classifications occur, and hence the name is also getting differed, like N-alkyl alkane amine we are saying. So to make the class of N-alkyl substituent only, they are asking frequently from amines. That's all the nomenclature of amines. Structure of amines. We know amines are the derivatives of ammonia. So when we discuss about the structure of ammonia, in turn we can discuss about the structure of amines. In ammonia, the nitrogen atom is sp3 hybridized. Just like methane, ammonia, water, all of them are the carbon, nitrogen, oxygen possess sp3 hybridization. But in ammonia, the nitrogen, it is a trivalent atom. That means it can make only 3 bonds. And it has one more unshared pair of electron over the nitrogen atom. Since atomic number of nitrogen is 7, so we can write 1s2, 2s2, 2p3. So this 2s2, 2p3 that becomes the valence shell of nitrogen. So these 2s and 2p orbital that mix together to form the sp3 hybrid orbital of one pair with one single electron. So we have 4 sp3 hybrid orbital of nitrogen. So in this case 3 of the single bond, that is it has 3 odd electron in sp3 hybrid orbital. Those 3 odd electron of nitrogen that can overlap with 1s1 orbital of hydrogen. Or instead of hydrogen, when you have methyl, the sp3 hybrid orbital overlaps with the sp3 hybrid orbital of carbon. So that ammonia, in case of hydrogen, the sp3 hybrid orbital of nitrogen can overlap with 1s1 orbital of hydrogen. So this makes the simplest form of ammonia. So in this case, the bond angle between nitrogen hydrogen is 107. Actually, it is lesser than 109 degree 28 minutes. This is what the tetrahedral bond angle. Because of sp3 hybridization, the tetrahedral bond angle will be 109 degree 28 minutes. But it is reduced to 107. Why the bond angle reduced? This is because of the possible interaction between lone pair bond pair electron and bond pair electron. In this, the repulsion between lone pair bond pair is greater than that of bond pair. So to minimize the repulsion between the lone pair and the bond pair, the bond angle gets reduced and hence it is reduced to 107 degree. Here all the 3 hydrogen atoms are simplest. So the hydrogen atoms, among them we do not find any interaction. But in the derivatives of ammonia, number of alkyl group increases from 1 to 3. So we have primary, secondary and tertiary. When you compare the size of alkyl, that becomes much larger than hydrogen. So in addition to lone pair bond pair repulsion, it may experience the bulky group with bulky group repulsion also. This is why, because all the CH3 groups, they have 3 shared pair of electron and other also has 3 shared pair of electron. So the repulsion among the shared pair gets increased. When it increases, then stability of the molecule decreases. So this is why, because when alkyl group gets increased in primary to tertiary, once again the bond angle increases 107 to 108 degree in order to minimize the repulsive interaction among the substituents of amines. So primary and secondary amine, the bond angle that do not differ greatly. But in tertiary amine, all the 3 alkyl groups are much larger enough. So because of the greater size, what happened? The repulsive forces will be maximum and hence the bond angle increases to minimize the repulsion. Therefore, that makes the molecule stable. So that's all the structure of ammonia and its amines. So ammonia, the nitrogen is sp3 hybridized, but in amines also nitrogen is sp3 hybridized, but the possible overlapping, it is depending upon primary, secondary or tertiary. If it is primary, the overlapping between sp3 hybrid orbital of carbon with 1s1 orbital of hydrogen, or if it is tertiary, the 3 sp3 hybrid orbital of nitrogen that overlaps with the 3 sp3 hybrid orbital of carbon. That's all. the structure of amines. Preparation of amines. Amines can be prepared by these different methods: Hoffman ammonolysis, reduction of nitro compound or reduction of nitriles, Hoffman degradation reaction, and Gabriel thalamide reaction. Let us see first of all Hoffman's ammonolysis of alkyl halides. So alkyl halides are RX. This alkyl halides, when it is treated with the ammonia, where ammonia it behaves as a nucleophile for the alkyl halide. So the halogen atom is also a nucleophile, and hence the halogen is substituted by the NH2 group. So this Hoffman's ammonolysis that follows nucleophilic substitution reaction. The reaction followed by this is nucleophilic substitution. Suppose we can have the reactions in two different ways. The one, I can have ammonia in excess, or the other one, I can have the alkyl halide is in excess. So depends on either the reagent or the substrate taken excess, we will get the different kinds of product. In case of excess of ammonia, that can form only the primary amine and the hydrogen halide. So here we can write this NH2 as NH3 as NH2H. So this hydrogen and halide will be removed. Therefore, the halogen atom is substituted by the amino group. We are getting primary amine, and no other products will be formed. But in the case of excess of alkyl halide, here the halogen atom is once again substituted by the amino group of ammonia. So I can write NH2H where NH2 behaves as the nucleophile. So this hydrogen halide is removed. So we are getting primary amine. See that the reaction, it has excess of alkyl halide. So when alkyl halide present excess, the reaction will proceed until all the alkyl halides are consumed in the reaction. So it would not stop up to the formation of primary amine, and it further proceeds to form up to the formation of quaternary amine. So this is what the main difference between the reaction with the excess of ammonia or reaction with the excess of alkyl halide. So with the excess of alkyl halide, we will get the formation of primary amine, secondary amine, tertiary amine, and quaternary amine. Once quaternary amines are formed, the reaction will be stopped. So in every case, the NH2 group, the hydrogen atom of each group is substituted by the alkyl group. So we are getting minus Hs, and one more alkyl group gets added up, and hence we have R2NH. If I have one more Rx, then there is minus Hx, I will get R3N. And in all these cases, that the primary amine, secondary amine, tertiary amine, they themselves behaves as a nucleophile for the subsequent steps. So when tertiary amine reacts with the one more alkyl halide, the lone pair of nitrogen atom that is simply given to alkyl group, that is the electrophile, and hence we are getting R4N plus X minus. It is said to be quaternary ammonium salt. So this Hoffman's ammonolysis, in which if alkyl halide is taken excess, we used to get the mixture of amines only. So this is what the disadvantage of this method. If you want to prepare only one kind of amine, where you have to take ammonia as excess. Okay. Suppose if I have the primary amine is produced, I have to extract the primary amine from the reaction mixture. What I can do? See, alkyl amine that has the hydrogen halide, the byproduct. This alkyl amine can react with the byproduct such a way. So I am getting RNH3X minus. So it is formed alkyl ammonium halide. So when this alkyl ammonium halide is hydrolyzed by a base, I can get sodium halide, alkyl amine, and with water. So primary amine can be formed even from alkyl ammonium halides. So that's all, by which we can prepare either primary amine or even the mixture of amine, depends on the reaction condition. The next one, reduction of nitro compound. Reduction of nitro compound already we discussed in nitroalkane and nitroarenes. So if the nitro compound is reduced by the metal acid as a reducing agent, then NO2 group is completely reduced to NH2 group. So nitro compounds are converted into amino compounds. So I am getting ethane amine from nitroethane. Similarly, this can be even extended for nitrobenzene. So when nitrobenzene is reduced by metal and acid, I will get aniline. So this is the most favorable method by which we can prepare the compound of amines from the nitro derivative. Then reduction of nitriles. So nitriles are CN group. So this C triple bond N can be reduced to CH2NH2. So for this reduction, you can take either lithium aluminum hydride or the catalytic reducing agent hydrogen nickel or even sodium amalgam in alcohol. Whatever be the reducing agent where the CN group is converted into CH2NH2. So how many hydrogen required? 4. So it involves the 4 nascent hydrogen atom for the reduction. At the same time, we can reduce amides also. Amide also reduced to primary amine. In this case, the CO group is reduced to CH2 group in presence of lithium aluminum hydride, where the oxygen is removed as water. So once again it requires 4 hydrogen atoms. So this is what reduction of nitriles or amides. By using either of the reducing agent, we will get primary amines. The reduction of nitrobenzene, if at all carried out in presence of iron and HCl instead of tin HCl, we will get once again that amino compound. So the NO2 is reduced to NH2. But the speciality of the reducing agent iron HCl is, in this case you can take only HCl to little amount. This is why, because when metal reacts with the acid, it forms hydrogen. This hydrogen is utilized for the reduction of nitro group into amino group. During the reaction, we are getting the byproduct of water. This water that hydrolyzes the ferrous chloride, iron 2 chloride into iron 2 hydroxide and HCl. So because of hydrolysis of the ferrous chloride formed in the reaction, once again produces hydrochloric acid. That's why this reaction, in which if you take iron HCl as a reducing agent, a little amount of HCl is sufficient, and they will say here the iron is taken in the form of scraps. Scraps means just like the waste material, iron itself taken as the reducing agent. The next one, reduction of isocyanide. We discussed about the cyanide. Cyanides are converted into primary amine, but isocyanides on reduction it gives secondary amine. Ethyl methyl amine is formed. So cyanide gives primary amine, isocyanide gives secondary amine. This reduction is carried out in presence of sodium, mercury and ethanol. So it requires 3 + 1 4 hydrogen. So this involves 4 hydrogen atom for the reduction. So in addition to the ammonolysis of alkyl halide with the excess of ammonia, this alkyl halide can also be treated with the sodium azide NaN3, where NaBr is being replaced. Br is replaced by the N3 group, so we will get ethyl azide. This ethyl azide, on further reduction, we will get the primary amine and nitrogen. Suppose if you have chlorobenzene, chlorobenzene can also be treated with ammonia, but in presence of copper 1 oxide at 200 degrees Celsius, we can write ammonia as HNH2. So the halogen atom nucleophile is replaced by the NH2 group. So we will prepare aniline. So the reaction conditions are very important when you convert aromatic compound into amine. Just like alkyl halide with the ammonia, we can prepare amines even from alcohol. So when alcohol is taken in excess with the ammonia in presence of the dehydrating agent alumina is used as dehydrating agent. See, in every case there will be a formation of water as a byproduct, that water being absorbed by the alumina. So we will get the mixture of primary amine, secondary amine, tertiary amine. So every case the hydrogen atom with OH of alcohol is removed as water. So we are getting subsequently primary amine, secondary amine and tertiary amine. Just like from alcohol, from phenol also we can prepare aniline, but it has to be boiled with ammonia at 300 degrees Celsius in presence of anhydrous zinc chloride, where the OH nucleophile is replaced by the NH2 group. So we are getting aniline. The next method of preparation of amines is Gabriel-Thalimide synthesis, in which you can prepare only aliphatic primary amines. And by this method you can't able to prepare aromatic primary amines because the aryl group does not undergo nucleophilic substitution reaction. This is one of the most important reasoning question. Gabriel-Thalimide synthesis is useful for the preparation of only primary aliphatic amines. By this method you can't even prepare secondary or tertiary, but primary can be prepared. And the primary aliphatic amines we can prepare, but aromatic amines cannot be prepared because this reaction involves nucleophilic substitution reaction. So such nucleophilic substitution reaction in the benzene ring is not possible. If you want to make nucleophilic substitution, it requires suitable conditions. So aryl group, as it does not undergo nucleophilic substitution reaction, aniline cannot be prepared by Gabriel-Thalimide synthesis. So in this the substrate is thalimide. Imide is the CONH group is called imide. So amine is NH2. If you have CONH2, that is amide. See, this CONH2 is amide. At the same time, if it has CONH, it is said to be imide. So when polyimide is treated with the potassium hydroxide, the presence of hydrogen that makes the compound acidic, and hence we will get a potassium salt of thalimide by the loss of water molecule. So in this, when we add a CH3Br, this CH3Br is an electrophile and the Br minus is the nucleophile. See, this electrophile that can be attacked by the nitrogen atom as it carries the negative charge. So we are getting potassium bromide and N-methyl thalimide. This N-methyl thalimide on further hydrolysis with potassium hydroxide, the bond between CONH group is broken. So they have two hydrogen. As it has two hydrogen, that makes CH3NH2, and the rest of the potassium KO group is added with the CO. We are getting potassium phthalate and primary amine, methane amine is formed. I have taken methyl bromide, so methane amine. If you take ethyl bromide, the product will be ethane amine. So suppose if you consider an aryl halide over here, if you imagine here I have taken C6H5Br. See that this benzene ring, it cannot be able to behave as a electrophile. This benzene ring that cannot be used as an electrophile because as well as this benzene ring does not undergo nucleophilic substitution reaction also. That's why we can't able to prepare aniline by this Gabriel-Thalimide synthesis. The next most important question, very most important question is Hofmann's degradation reaction or Hofmann bromamide degradation reaction. Degradation means decreasing. Bromamide, a bromamide is formed as an intermediate during the reaction. The mechanism let me explain later. Now let us see only the reaction, how amides are converted into amines. See, by this method you can able to prepare only primary, but both aliphatic and aromatic amines can be prepared. So Hofmann process, Hofmann degradation reaction is useful for both the preparation of primary aliphatic amine as well as primary aromatic amines, but you cannot able to prepare secondary or tertiary amines. See, acetamide, when it is treated with the bromine and the potassium hydroxide, this is what the reagent required for the Hofmann bromamide reaction, where CO group is converted into potassium carbonate, and the bromine with the potassium, it forms potassium bromide, and the oxygen with the OH, that makes water. So we are getting only CH3NH2. We are getting CH3NH2. So from the amide, you remove the CO group, you will get the rest of the product. So from acetamide, instead of CO, if I find the group is CH3NH2. Similarly, C6H5NH2. You just hide the CO group, carbonyl group, you will get C6H5NH2. So aniline is formed. So this carbonyl group only removed as potassium carbonate and water along with the potassium bromide. So to balance, 2 potassium, 2 bromine, 2 KBr, K2CO3, so 2 potassium, so potassium hydroxide becomes 4 times, and 4 OH with the 2 hydrogen, that makes 2 molecules of water, and the CO group is converted into CO3. That's all the different methods of preparation of amines, both aliphatic as well as aromatic amines. Okay students, let us close our today's session, and we will continue the same topic in our next session. Until then, bye bye.